Introduction. This section gives an intuitive background to graph theory. A graph is made of vertices, points, and edges, lines connecting them. The degree of a vertex is just the number of edges touching it. We learn about different graph types. Simple graphs, no loops, edges from a vertex to itself, or multiple edges between the same two vertices. Directed graphs, digraphs. Edges have a direction, shown with arrows. Key ideas are also introduced. Walks, paths, and cycles. A walk is a sequence of edges, a path doesn't repeat vertices, and a cycle is a closed path. Connected graphs, all in one piece. Trees, connected graphs with no cycles. Planar graphs can be drawn flat without any edges crossing. Chapter 1. Definitions and Examples. This chapter gets more formal. Key terms. Two graphs are isomorphic if they have the same structure. A connected graph is one where you can get from any vertex to any other. If not, it's disconnected and made of separate components. The handshaking lemma. A fundamental rule states that if you add up the degrees of all vertices, the sum will be an even number, exactly twice the number of edges. This means there must be an even number of vertices with an odd degree. Types of graphs. Complete graphs, Kn, every vertex is connected to every other vertex. Bipartite graphs. The vertices are split into two sets, and edges only connect a vertex from one set to one in the other. Regular graphs. Every vertex has the same degree. Chapter 2. Paths and Cycles. Here we dive deeper into how we move around a graph. Connectivity. A graph with n vertices is always connected if it has more than half n-1 times n-2 edges. The distance between two vertices is the length of the shortest path connecting them. Eulerian graphs. A connected graph is Eulerian if you can draw it without lifting your pen, covering every edge exactly once and ending where you started. A key theorem says this is only possible if every single vertex has an even degree. If exactly two vertices have an odd degree, you can still cover every edge, but you'll start and end in different places, semi-Eulerian. Hamiltonian graphs. A graph is Hamiltonian if it has a cycle that visits every vertex exactly once. Finding these is much trickier than finding Eulerian paths. One rule of thumb is that if a simple graph with n vertices, where n is at least 3, has every vertex connected to at least half of the other vertices, n by 2, it's guaranteed to be Hamiltonian. Applications. Shortest path problem. Finding the quickest route in a weighted graph, like GPS navigation. Critical path problem. Used in project management to find the longest path, which determines the minimum project completion time. Traveling salesman problem. Finding the shortest possible route that visits a set of cities and returns to the origin. This is a famously hard problem to solve efficiently. Chapter 3. Trees. This chapter focuses on trees, a simple but powerful type of graph. Properties. A tree is a connected graph with no cycles. Any two vertices in a tree are connected by exactly one unique path. A tree with n vertices always has exactly n-1 edges. Spanning trees. A spanning tree is a subgraph that includes all the vertices of the original graph, but is a tree, no cycles. You can create one by removing edges from a graph until no cycles remain. Counting trees. A famous result shows that the number of distinct labeled trees you can make with n vertices is n to the n-2. Applications. Minimum connector problem. Finding the cheapest way to connect a set of points, like laying cables. A greedy algorithm works well here. Just keep picking the cheapest available edge that doesn't form a cycle. Searching. Trees are fundamental to search algorithms, like breadth-first search, exploring layer by layer, and depth-first search, exploring one branch as far as possible before backtracking. Chapter 4. Planarity. This chapter is all about graphs that can be drawn flat. Planar graphs. A graph is planar if it can be drawn on a 2D surface without any edges crossing. The complete graph with 5 vertices, K5, and the utilities graph with 2 sets of 3 vertices, K3, 3, are the 2 fundamental non-planar graphs. Kuratakovsky's theorem. This is the master rule for planarity. It states that a graph is planar if it doesn't contain a version of K5 or K3, 3 hidden inside it. Euler's formula for plane graphs. For any connected planar graph drawn on a plane, the number of vertices, n, edges, m, and faces are related by a simple, powerful formula. N minus m plus f equals 2. This can be used to prove that certain graphs can't be planar. Dual graphs. Every plane graph has a dual. You create it by putting a vertex in each face of the original graph and connecting 2 new vertices if their faces shared an edge. Cycles in the original graph become cut sets, edge sets that disconnect the graph, in the dual, and vice versa. Chapter 5. Coloring graphs. Graph coloring is a fun topic with serious applications in scheduling and logistics. Vertex coloring. A graph is K-colorable if you can color its vertices with K colors so no adjacent vertices share a color. The minimum number of colors needed is the chromatic number. A graph is 2-colorable if and only if it's a bipartite graph with at least one edge. Coloring planar graphs. For planar graphs, it's known that you never need more than 6 or even 5 colors. The famous 4-color theorem states that every simple planar graph is 4-colorable. This was one of the first major theorems proven with the help of a computer. Edge coloring. You can also color edges. The minimum number of colors needed to color the edges so that no 2 edges touching the same vertex have the same color is the chromatic index. Chapter 6. Matching, Marriage, and Menger's theorem. This chapter covers topics related to pairing of vertices and finding robust connections. The marriage theorem. This theorem provides a simple condition to solve the marriage problem, matching a set of boys to a set of girls they know. It states that a complete matching is possible if and only if every group of K girls collectively knows at least K boys. Menger's theorem. This powerful theorem relates path disjointness to connectivity. In its edge form, it says the maximum number of edge disjoint paths between 2 vertices is equal to the minimum number of edges you need to cut to separate them. The vertex form is similar but deals with vertex disjoint paths and vertex cuts. Network flows. This applies graph theory to networks like pipes or data connections. The goal is to find the maximum flow from a source to a sink. Max flow min cut theorem. A cornerstone of network theory, this theorem states that the maximum possible flow from a source to a sink is exactly equal to the capacity of the tightest bottleneck in the network, the minimum cut. Chapter 7. Matroids. This final chapter introduces a more abstract structure that unifies many ideas from earlier chapters. What is a matroid? A matroid is a structure that generalizes the idea of independence. It consists of a set of elements and a collection of its subsets called bases. These bases behave like spanning trees in a graph or bases in a vector space. Duality. Every matroid has a dual matroid. This abstract concept of duality elegantly explains the deep connection between cycles and cut sets in graphs. A graph's cut set matroid, where cycles are cut sets, is the dual of its cycle matroid, where cycles are normal graph cycles. Matroids and planarity. Matroid theory provides a high-level way to understand planarity. A graph is planar if and only if the dual of its cycle matroid is also a graphic matroid, meaning it can be represented by a graph. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.